presentations, and the first one is going to be given by Steve Kai, whom I've seen on the list of attendees, so I know he's there. But Steve, could you actually share screen while I give introduction, please? And unmute yourself and show your video if you wish. Steve is the coordinator of the Structures Group at Louisiana State and is holder of the Edwin B. and Norma S. McNeil Distinguished Professorship from 2010 onwards. He got his BSc, his MSc and his PhD degrees from Zhejiang University, Tsinghua University and the University of Maryland. His research interests include bridge performance evaluation, hazard mitigation of coastal infrastructures and vehicles under wind wave action, and long-span bridge aerodynamics. He's served on many editorial boards and technical committees. Other major professional services include having served as Secretary and Treasurer of the American Association of Wind Engineering for more than 10 years, which must have seemed like a lifetime. So I'm going to hand over to Steve now, and it's good to see you, Steve. Again, I'd remind you, if you wish to leave any questions for any of the speakers, could you put it into the chat function, please, where Grace will be collating it. Over to you, Steve. Thank you. Could you unmute yourself, Steve?
Is it okay now?
That's fine.
Can I start now?
That's fine.
Hi, Chris. Thank you for your nice introduction. Good morning, everyone. It's my early morning. Today, I'm going to talk about time domain simulation of turbulence effects on the aerodynamic flood of long-span bridges. First, I can start a little bit of the background. We have been studying the turbulence effect on bridge flood for many years. And if the effect is beneficial or harmful, still remains a debate. Generally, we have three approaches to stop the wind turbulence effect on bridges. First, we can do the experimental observation, and then we can use the frequency domain approach or time domain approach. So in this short talk, I will briefly touch this method and discuss this method use a prototype bridge. Here, I'm not going to talk about the safety approach. This is the bridge I'm going to use in the following discussion. It's a suspension bridge with a main span of about 800 meters, and it's a box girder section. This just shows some of the dynamic properties with the mode shape and modal frequency, first vertical, symmetric, and the first anti-vertical and torsional mode shape. To start the turbulence effect, we can always start with the experimental observation. For example, we can use a section model, then we can observe the flood behavior directly. Of course, to some extent, we cannot observe the overall flood performance of the full bridge. And then we can also measure the flood derivatives in the turbulence flow and use this information in the full bridge analysis. Or we can observe the behavior, use the full model directly. But based on the observation, we know the turbulence is generally beneficial to flood behavior, but not always. As I said, it's still a debate. The issue is the turbulence characteristics cannot truly match in the lab. For example, the integral length is an issue. We cannot duplicate the large enough integral turbulence length in the typical wind tunnel. Then we can use the frequency domain analysis. We can start with in the lambda flow. This is the typical vibration, the equation of motion for bridge vibration. This side is the self-excited force for flood analysis. This is an example of the self-excited force. We can use the linear format in the time-free time friction domain. The typical work is by Dr. Scalan. So this is the sample example by use the prototype bridge information. We can use the eigenvalue analysis, and based on the real part becomes 0, we can identify the flutter velocity, and also we can use the imaginary part. We can identify the oscillation frequency. Then we can also start the flutter in the turbulence flow. So typically in this frequency domain approach, we can use the same procedure as used in the lambda flow, except we use the flutter derivatives measured in the turbulent flow. Now the argument is, can this true effect of turbulent flow or turbulence be reflected by these measured flutter derivatives due to reasons we mentioned, because the mismatch between the lab and the field of parameters such as the integral length and also the nature of the flutter derivatives. For example, we make a small deformation and also linearity assumption in this approach. So this still remains a debate if this can truly reflect the effect. Then we can move on, move to the time domain analysis. We know the time domain analysis is convenient to be incorporated with the finite element analysis, and they can also deal with all the nonlinear issues more conveniently. And also we can deal with the nonlinear aerodynamic force, even though I'm not going to talk about the nonlinear aerodynamic force model here. So again, we start with the lambda flow. We can express the self exact force in a linear format in the time domain by use the impulse response function. And static force can be eventually to be expressed in this kind of format by introducing the so-called rational function. The typical works by Dr. Chen and Dr. Krim. So by using the typical flutter derivatives, we can identify the coefficient A1, A2, A3. So we can express the force in the time domain. So this is a typical results or sample results from the prototype bridge. By time domain analysis, we can calculate the amplitude of the motion. So this is under 79 meters per second. We can see the amplitude become constant, but under 80 meters per second, the amplitude become divergent. So from here, we can identify the flutter critical velocity is about 79 meters per second in the time domain analysis. Then we can start with the, we can consider the turbulence flow. So we have different procedures we can follow. So the first procedure, we can use the same procedure as in the lambda flow, except we can use the flutter derivatives measured in the turbulent flow to identify the rational function. Nothing else is different, just use different flutter derivatives. But the arguments still remain. As we talk in the frequency domain, can this flutter derivatives measured in the wind tunnel truly reflect the turbulence effect on flutter behavior? Now, the second procedure, we can divide the frequency into high frequency and the low frequency components. So for the low frequency component, we can use it to calculate so-called equivalent wind attack angle, such as this, like it have a statical part and have a turbulence part. But for the high frequency component, we can treat this the same as in the previous one by use the measured flutter derivatives to calculate the coefficient time domain. Now the issue is how do we divide this high frequency and low frequency, and if this linear superposition principle valid in this calculation. Then the people also use the so-called procedure 3 here. It's a random parametric excitation, or PRE. For most people, maybe most people are maybe less familiar with this method. So basically, in this method, we treat or we introduce the turbulence directly in the surface side force like this. So the wind velocity have two components. One is uniform or average velocity, one is the turbulence velocity. So by using this in this equation, then the equation become random parametric excitation type of problem. In this approach, we can use the Froth derivatives in the laminar flow. So this is an attractive feature. So we can reduce the measurement work in the tunnel. And the results show the high intensity turbulence could be harmful for the Froth velocity. So this is kind of different from most of the lab observations. So the issue in this method is only the along wind turbulence is included, like here, right? This is along wind turbulence. The vertical turbulence is not considered in this approach. And this results in very complicated RPE theory. We need to use the stochastic differential equation to solve the problem. And we need to reduce the work, we need to assume the wind is a wide noise process. And the Froth is based on the statistical moment instability. This is not convenient for the final element formulation and engineering application. And also some people question if this approach can really reflect in the fluid stroke interaction mechanism. Then we move on the so-called procedure 4 here. This is the proposed analysis in this study. So it's kind of like a time domain numerical RP analysis. So in this approach here, we use the similar approach to the previous RPE analysis. The along wind turbulence is introduced directly in the self-excited force, but the vertical turbulence is indirectly used to calculate the equivalent attack angle of wind, like this. You have like a statical part and have a turbulence part, and the Froth derivatives we can use the in the laminar flow because all the turbulence effects are reflected in this part, so we can purely use the laminar flow measurement. So we can reduce the again we can reduce the labor work. But in the time domain step-by-step analysis, we can update the parametric, other dynamic parametrics for each equivalent attack angle. And we need to make assumption for the white noise process. And this can be community incorporated in the final element analysis. Again, the issue is can this approach really catch the true effect of turbulence? We need a direct validation. And next, I want to show some preliminary analysis based on this proposed approach. We consider 4 different turbulence, 5 to 20%. This is a wind turbulence sample at the midspan and the cross span of the bridge. To start the turbulence effect on the bridge, we start the correlation. We compare the correlation on the laminar flow and the turbulent flow. So in the laminar flow, we can see the correlation between midspan and the cross-span response is much high. So we take the correlation based on different methods. So we can see in the laminar flow, the correlation is very good. But in the turbulent flow, because the turbulence, the random nature of turbulence, the correlation is actually negative here. This slide summarizes the results of the turbulence effect on the Froth behavior. We can see as the turbulence increase, the Froth velocity increase monotonically. So the lowest ones in the laminar flow, and then on each wind attack angle, the turbulence increase as the turbulence intensity increase. We believe that the stabilizing effect of the turbulence is due to the decorrelation, as we present in the last slide. The correlation is different on the laminar flow and on the turbulent flow. But I need to note it, in this preliminary analysis, we did not update the flutter derivatives and each equivalent wind angle because we don't have all the measurement of the flutter derivatives and each attack angle. But it demonstrates that turbulence, the effect can be conveniently incorporated in the finite element time domain step-by-step analysis. We can reduce the previous very complicated RPE analysis. A little bit of summary and comments. We know the frequency domain analysis is much less expensive. It's a much more straightforward. Time domain can handle all kinds of nonlinear issue. It's more powerful. The turbulence can change the vibration pattern and it can weaken the spatial vibration correlation. That may be the main reason of its stabilizing effect. In other words, it increases the flutter velocity. But validation methodology of the methodology is really needed, but it's very difficult. We need to carefully design experimental work to directly verify the turbulence effect by using realistic parameters. Because of the time limit, I can stop here just very briefly to introduce some my recent work. Thank you.
Thank you very much indeed, Steve. As I say, we will take questions together at the end. So could I ask you now to unshare your screen, and could I ask Claudio Manini, please, to share his while I give an introduction for him. Claudio Manini is assistant professor in the Department of Civil and Environmental Engineering at the University of Florence in Italy. He received his PhD in 2006 and received the ANIV, that's the Italian Wind Engineering Society Award, in 2008, the IAWE Junior Award in 2011, and the EASD Junior Research Prize in 2014. His main research interests are in bluff body aerodynamics and wind-induced vibrations from a theoretical computation experimental point of view. And he writes personally, since his PhD, he's always been enthralled by the aerodynamics of long-span bridges. So if Claudio is there, please, if you could share, and if you could share your screen as well, and your demute yourself. And it's nice to see you. Thank you.
Hi. Thank you very much. Well, I cannot share the screen.
Yeah, I have. Because, I need to unshare. I need to go back to my full screen. I have trouble here. Let me see.
Have you opened PowerPoint?
Yeah. Let me see how to. I need to go my full screen. I cannot find how to go back to my full screen.
Claudio, could you could you email me your presentation, or is it too large?
I don't know. Let me see.
Steve, I think you can unshare your screen by going to the Zoom.
Yeah,
and then
I couldn't
there
find
is
the
in
button.
the top and the bottom.
One voice at a time, please. Marja, you're saying something?
Yeah, I'm just saying how to unshare the screen. You go to the Zoom app, and then you press either in the top or in the bottom. There's an unshare button.
I cannot exit either, so I know what's going on. Okay, I just turn off my computer.
Okay, Claudio, are you on sharing? Steve, could you, it still says we're sharing your screen, Steve.
Yes.
Okay.
Could you come out, please?
I'm going to log out. Whoa.
Okay, Claudio, could you try again?
Yes.
Right, we're there with you.
Yeah.
Okay.
You see it?
Apologies for that. I think Steve had left his screen on, and that was why.
Yeah.
Okay, over to you.
Yeah, thank you very much. Hello, everybody. Sorry for this delay. So I'm talk briefly about nonlinear modeling of self-excited forces for a long-span bridge under turbulent wind. Now, just a brief introduction. Actually, the understanding of the dynamic behavior of bridges under a turbulent flow is a complicated issue, we all know. One of the reasons for that is that most of wind tunnel tests are still carried out in smooth flow. And this is also due to the fact that it is quite difficult to reproduce the correct turbulence at the scale of a large scale of the sectional models that normally are used. And of course, we are expecting a great improvement from the increasing full-scale measurement that we see now. Anyway, if we concentrate on bridge buffeting analysis, normally these are based on several simplifying assumptions. And the consequence of that is that sometimes, often, let's say, the agreement with full-scale measurements is not satisfactory, and we see some space of improvement. And one of the important problems we see in buffeting, a nonlinear effect, is the fact that large-scale turbulence is able to produce a high amplitude and low frequency angle of attack. And this time-varying angle of attack produce a modification of the aerodynamic properties of the bridge deck. For instance, just to give a brief explanation, if we look at this time trace of the angle of attack measured at a certain site, and we take the low frequency part, basically we see that considering the static force coefficients, we are going to span this range of angles of attack, and we see that in this range, actually the force coefficients have a nonlinear trend. But more than that, we are particularly interested in the effect of this time-varying angle of attack on the unsteady self-excited forces. And for instance, if we look at the flutter derivatives that we measured for this twin box deck in the range of mean angles of attack between -5 and +5 degrees, we see a huge variation of the derivatives of the coefficients with the mean angle of attack. There are some coefficients that even change sign in this range, which is not huge range. And in particular, for instance, if we look at the coefficient A2, we see that the variation is very important, and this coefficient we know is related to the aerodynamic damping torsion, so it's very important. Now, the effect is clear that there can be an effect of this time-varying angle of attack, and we would like to study that. Well, of course, this is not nothing new, because this problem has first been focused by Professor Diana and the group at Politecnico di Milano since the 90s. And since then, many models were proposed to address the problem. In particular, an elegant and also computationally efficient model was proposed at the beginning of the noughties by Chen and Karim. And this model was based on the rational function approximation of the transfer function of self-excited forces, basically with an expression like this, where the G function is the transfer function based on flutter derivatives. Now, all these methods are time domain approaches, and they are basically based on the concept of band superposition. That is, on the idea that we can separate the low frequency turbulence, which is responsible for this, which is produced this large variation of the angle of attack at low frequency, and high frequency turbulence, which instead is treated in a linear way. And the second basic assumption that is normally used is the linearization around the slowly varying angle of attack. Okay, in this work, we reconsidered the model proposed in 2003 by Chen and Karim, because as we said, it was particularly clear, simple, and efficient. And in particular, we noted that for a reliable estimation of the buffeting response of a bridge, it is very important to have an accurate rational function approximation of the transfer function. And therefore, we introduced a modification in the way the rational function approximation is determined. In particular, we consider it from the real beginning as a multivariate function of both reduced velocity and slowly varying angle of attack. Basically, we ended up with a time variant model which can be formulated in the state space. And if we look then at the approximation of the flatted derivatives based on the rational function, we can see that here we are reporting just a few examples, but the flexibility of the approximation is very good, and so the approximation with experimental data is also very good. This is the first thing we reached. An important part of the work was a wide experimental campaign that was carried out in the wind tunnel of the Norwegian University of Science and Technology in Trondheim, Norway. And there, two sectional models were tested. The first one reproduces the single box deck of the Harlanga Bridge in Norway. And the second one is a twin box deck, which was important because it shows more nonlinear features as we were expecting. Now, the experiments were not just aimed at measuring flatted derivatives for various mean angles of attack, as we saw a few slides back, but we wanted to quantify in a simple way the effects of the slowly varying angle of attack on the self-excited forces, and also to validate the time variant model we set up. In order to do that, we conceived some biharmonic tests, some biharmonic force tests, force vibration tests, or even multi-harmonic actually. In these tests, basically we are imposing to the model low frequency pitching motion at large amplitude, and superimposed to that we have a high frequency small amplitude vibration, pitching vibration, or also a hip vibration, a sway vibration, or a combination of the 3 degrees of freedom. Clearly, a very important parameter in this kind of experimental analysis is the frequency ratio of the so-called fast motion to the slow motion, as we will see in a moment. Okay, we impose this force motion, and if we measure the time history of the self-excited forces, and as reported, for instance, here, and here we are concentrating on the high frequency components in particular, the one we are interested in, we see that the modulation of the self-excited forces in time due to the slowly varying angle of attack is clear. Nevertheless, in order to quantify the amplitude variation and above all the phase shift variation, because it is very important because it means damping, the amount of damping, and the sign of damping as well. So in order to do that, we applied the Hilbert transform of the time history of the self-excited forces. And in this way, for instance, these results are shown for a superposition of a high frequency pitching motion and a low frequency pitching motion. And in this case, these results are for twin box deck, and here we have a frequency ratio of 8.5. And clearly, the effect of the slowly varying angle of attack is really clear on the self-excited force. We see the variation of the amplitude and the variation of the phase in time, even the sign change of the phase. And for instance, there are at some time we have that the aerodynamic moment is anticipating the pitching motion, so we have negative aerodynamic damping. So which is of course very important to take into account. The other thing we can see is that the the numerical model, which is that we call a 2D RFA model, so the red line, follow very closely the experimental results. We are the gray line, both in terms of amplitude and in terms of phase. And well, of course, the classical linear time invariant model is not able to reproduce these features. This is obvious. Now, a very important point is that the basic assumption that stands behind this model, like other models, is the fact that the angle of attack varies slowly. And this can be a strong limitation. Nevertheless, what we observe in the test is that the model seems to be applicable even when the fluctuations of the angle of attack are not so slow. For instance, here we have a limit case where we imposed a frequency ratio of 1.7. So the low frequency motion is just 1.7 slower than the high frequency motion. In this case, we cannot plot for practical reason the Hilbert transform, unfortunately, because it was more intuitive, the result, but still we are showing the real and the imaginary part of the Fourier spectrum. And we see that the agreement between numerical results and experiments is still very good. So we were quite satisfied because this means that the model can be used for practical applications. Now, after that, the question arises, so does this time variant behavior of self-excited forces have a significant effect on the buffeting response of a full bridge? Let's say that from a certain point of view, the extension from the mathematical point of view, the extension of the time variant model to a realistic bridge full structure is relatively easy. It's not a big problem. Nevertheless, there are two issues that are crucial that we would like to highlight here. The first one is that the quick loss of span-wise coherence of the turbulent fluctuations is supposed to attenuate the modulation of self-excited forces due to low frequency turbulence. And this seems to be confirmed by the first results we obtained on full bridge structures. And the second point is that the way to separate the low frequency and the high frequency bands, which is the basic of all these band superposition methods, has an effect, an important effect. And how to do that and is still, let's say, an open issue on which we have to pose much attention. Finally, I wanted to say that this work is being developed in collaboration between the University of Florence and the NTNU of Trondheim, Norway, in particular with Professor Ole Oiset, that I thank a lot. And special thanks go also to Niccolò Barni, that during his PhD thesis did an impressive amount of work on this topic. So thank you very much for your kind attention.
Thank you very much indeed, Claudio, and for that wonderful introduction to our next speaker. In fact, could I ask you then to unshare your screen, please? And could I ask Professor Oiset to share his screen while I read his introduction for him? Ole Oiset is a full professor in structural dynamics at the Department of Structural Engineering at the Norwegian University of Science and Technology. He's head of the Structural Mechanics Research Group and the educational coordinator of the study program in Civil and Environmental Engineering. The dynamics of structures subjected to environmental loading is his main research field, and he's got a research interest in stochastic dynamics, wind engineering, marine engineering, structural reliability, and health monitoring. He's supervised 20 PhD candidates and 80 master's students since about 2012. So if I could ask Professor Oiset to show himself and to unmute and deliver his presentation on lessons learned from long-term wind and acceleration modeling of the Harlanga Bridge. Thank you.
Yeah, thank you for the introduction. Can you hear me well?
Yes, we can hear you. Well, yes, that's fine.
Yeah, thank you. Yeah, so I would like to share some of the lessons that we have learned during our monitoring project. So the Harlanga Bridge is the longest suspension bridge in Norway. It has a span of 1,308 meters and is surrounded by very complex terrain. And it's also very strong winds, at least compared to a Norwegian scale at the bridge site. Here you can see a map of the local topography. You can see the bridge here, and you can also see the contours of the mountains surrounding the bridge. And the highest mountains are about 1,500 meters high, and it's a very rapid change in elevation. Here you can see two pictures taken from the bridge deck facing east and west. And as you can see, the terrain is very complex and will have a significant influence on the turbulence characteristics. So just after the bridge was opened in 2013, we got funding to install a comprehensive monitoring system on the bridge. So it consists of 20 triaxial accelerometers distributed along the girder and in the two towers. It's 9 wind sensors that are distributed such that it's possible to study the spatial properties of the wind fields. And the sensors are connected to data loggers that communicates through a wireless network, and the data is eventually pushed to the servers at NTNU. We have just now published an open access dataset where all the data we have recorded is available and can be used freely by the research community. So you can access it through this unit bird data repository by just clicking on this link. And we have also just got accepted a paper in the Journal of Structural Engineering describing the dataset. And we have spent quite some time preparing the datasets. We hope that some of you will find it useful for your research purposes. We have spent a lot of time trying to organize the big dataset according to the user's need. Raw data is available, adjusted data with high sampling rate, and also adjusted data with 10 Hertz and 2 Hertz sampling rates to make them more convenient to handle. We have also gathered special datasets as storm events, continuous recording with low wind speed in case you would like to do operational model analysis studies or traffic-induced vibration studies, recording with highest wind speeds, and also recording with the highest dynamic response. Yeah. So then I would just like to scratch a bit on the surface on the lessons that we have learned. And here you can see 2 classical plots. This is the standard deviation of the horizontal response, and this is the standard deviation of the vertical response at the midspan. The blue and black curves here, they are response predictions using classical multimode theory. The gray dots are standard deviation of measured accelerations, considering an averaging period of 10 minutes. And as you can see, we underpredict the response quite much for many of the measured recordings. And you can also see that we have also a very large scatter. And our research shows that most of the scatter you see here is caused by variability in the properties of the wind field. So we have different turbulence properties, for instance, at the same mean wind velocity and so on. To improve design predictions, we have proposed a probabilistic turbulence model. And that's based on a very simple wind field model that's typically used in design. The only difference now is that the parameters in the model is given by a joint probability density function. And we have found that it's very convenient to use, for instance, a variable distribution for the mean wind velocity, and then combine it with a joint log normal distribution for the other parameters, because it fits reasonably well, and it's very convenient to fit a joint log normal distribution to data when you have many parameters. Lesson number 2 is that maximum response might not occur at the maximum wind speed. And you know, the normal thing to do in wind engineering is to take the mean wind velocity with a certain return period, for instance, 50 years or 100 years, calculate the dynamic response, and use the expected peak value for your design. Another approach is to use the full long approach, term approach, where you consider a longer period, for instance, 1 year, and then you can take into account the different wind conditions that will take place during the long-term period. This is kind of a computationally demanding approach. So a simplification is to use the so-called environmental contour method, where you identify combinations of the environmental parameters with, for instance, 100-year return period. You can see an example of a 2-parameter case here. Here you can see the contour, which is basically then combinations of parameters. All points along this contour has 100-year return period. And then you can check your response along the contour and identify the place where you have the maximum response and use that for your design predictions. Here you see a 3-dimensional case, then you get a contour surface. You check the points on the surface, and you identify where you will have the highest response. The third lesson is that non-stationary events might govern the design or be a very critical thing to consider. And this is a finding that was very much inspired by a guest lecture that John Owen gave at our university when he discussed the results that he had discovered for the Fort Road bridge. And we started looking in our data set to see if we saw something similar. So this is a recording, a 7-hour recording, where it's quite a severe storm, the storm Thor, in January 2016. And the colors here, they indicate the horizontal wind speed, mean wind velocity plus turbulence, and you can see the different sensors along the bridge deck down here. And this middle graph here shows the recorded velocities together with a 3-second moving average and a 10-minute moving average. And the bottom figure here is the response. And as you can see, we have a very severe response with short duration here. And that corresponds to this ridge that we see here on this plot. So we had a very sudden increase in wind velocity that covered a very large part of the span of the bridge, and that resulted in a very severe dynamic response. You can also see the measured wind speed here for all wind sensors. That's with a 3 seconds averaging period. That's the red curves. You can see the 10 minutes mean here. And here you can see there's quite some seconds where the 3-second averaging period for most of the sensors raised up to 40 seconds, 40 meters per second in a very correlated manner. And this gives the bridge quite a push in the horizontal direction. And we looked at the weather radar during this particular event. And what we saw was that there was a very heavy rain passing the bridge site during this non-stationary event. The last lesson is that damping might be lower than you think. Damping levels seems to always surprise us on some occasions. There's also quite some severe hanger vibrations at the Harlanga Bridge site. You can see a wavelet transform of hanger vibrations here. And you can also see the dashed line is the mean or the wind velocity. And as you can see, the vibrations, they jump from mode to mode as the wind velocity changes and the excitation frequency due to vortex shedding is changing. And this was kind of unexpected because, you know, according to normal design guidelines, the hangers should be fine. But what we see is that here is a damping for the different frequencies, natural frequencies of the structure. And as you can see, we have reasonably high damping for low frequencies, but the damping decreases and decreases as the frequency gets higher, and then eventually you get a damping that is so low that you will end up having vortex-induced vibration problems of your hangars. And what's so special with high-frequency vortex vibrations is that it takes a very short time before you reach lock-in. So it's and that's why you see this jumping effect here, where you have lock-ins for several vibration modes for several velocities. So by that, I would just say thank you for your attention, and thank you very much for inviting me, and also thank you to Professor Chris Baker for arranging these seminars. I think it's a very great initiative. So thank you very much.
Thank you very much, Ole. Quite fascinating. I might have things to say at the end on that. Which brings us to the last of our presentation. So if I could ask you to take your screen off, which you have, and ask Luca to share his screen. Luca Cariacoglu is an associate professor in the Department of Civil and Environmental Engineering of Northeastern University in Boston. His research interests are in structural dynamics, random vibration, wind engineering, fluid structure interaction of civil engineering structures, linear and nonlinear cable network dynamics, wind-based energy harvesting systems, and wind energy. He received the NSF Career Award in 2009 and was elected a Fellow of the ASCE in 2020. And he doesn't say so, but he was also the co-chair of the PBAA in 2016. So if I could hand over to Luca for the last of our presentations today, please.
Thank you, Professor Baker. Thank you for the kind introduction, and I hope you can all hear me well. Welcome, everyone.
We can hear you okay.
Yes, thank you. So also I would like to thank Professor Owen for inviting me as a contributor to this lecture, to his lecture. So the presentation is going to be about, if you want, I divided this presentation in 4 parts or 4 lessons by borrowing from previous speakers. And the research motivation is clear from the title. So I will be dealing with a topic which has been important to me, which is effects of uncertainty and uncertainty propagation and error propagation on bridge, long-span bridge response. So I have prepared 4 parts and 4 different approaches that I'm going to briefly introduce to you in various cases related to both buffeting analysis and flutter analysis. So what's the motivation for my research, or the research that we've been doing over a number of years, I have to say? We were interested in fluid structure interaction of long-span bridges for the longest time. And we realized that characterizing fluid loading and forces relies on models and experimentation. And usually, wind tunnel test is carried out to do so. And one of the issues that we learned over the years that as an important issue is the fact that perhaps experimental error should be considered or maybe important in this type of analysis. And as was mentioned by one of the earlier speakers, Professor Tsai, one of the way we could consider to represent this type of errors is through parametric perturbation or some sort of perturbations. So I am going to discuss essentially how one can essentially introduce or have this problem resolved, both from the point of view of the buffeting response and how this perturbation affect both buffeting and ultimately flutter response with the ultimate goal of improving the performance of the bridge. So I'm going to present some analytical and numerical results. So the first part, or the first contribution, is a contribution that we did in the field of so-called semi-analytical solutions through stochastic calculus. So we got interested in this field of stochastic calculus a number of years ago, and so and it was already introduced by a former speaker. Somehow the issue, Professor Tsai, who in the past actually has used this approach, and among others also Gianni Bartelli in Florence. And we make use of the standard tools. The standard tool for me is, of course, the unbeatable multi-mode approach that was relies on Professor Scanlan's idea or ideas. And so the elastic loads and the turbulence-induced loads based on the eventually the multimode theory. But also, in order for me to solve this problem from an analytical point of view, what I need to do, I need to introduce some simplifications. And to be able to solve the problem using this type of Markov, so-called Markov model, what I need to do, I need to have a linear structure, which is something that is usually the case, at least for buffeting analysis. I have to look at couple mode, in this case, flutter or buffeting. I'm missing buffeting here, where I am essentially concentrating the interest on two modes, like, or two predominant modes, a vertical mode and a torsional mode. We can debate about them. We can also make the turbulence non-Gaussian, and this was something that was mentioned by an earlier speaker, by appropriate tuning of the turbulence. And we may need to rely on the so-called elastic states as a function of time. In this case, my time is the standard time of the standard dimensionless time. But in order for me to solve the problem from a semi-analytical point of view, I need to simplify things a little bit more by using essentially buffeting, in the case of buffeting, span-wise modal correlation length. And the idea came to me numbers of years ago, and it was due to another pioneer in wind engineering, Professor Solari, who unfortunately passed away recently. And the idea is to separate, or to break the problem from a partially correlated problem in space to a fully correlated load over a reduced length of the deck in this particular case. So in order for me to solve the problem, I need to use state space representation, which was mentioned by other speakers. The novelty, if you wish, is this part delta. So apart from the standard variables, so the response variables of the bridge, the turbulence effects, or eventually the turbulence states that are needed to somehow make the turbulence compatible with the actual spectrum of the turbulence, I need to use an augmented vector of random variables in a similar way to what was done by other investigators. The interesting thing is that if I use this formalism, I can essentially rewrite the problem into a stochastic differential equation system, which is a system where the input is a white noise. The system is written in terms of in a non-differential form, but it's in an incremental form because of the fact that the derivative formally of the Wiener process or the Gaussian process does not exist. And I can use two things to my advantage. The first is that when I deal with buffeting response, if I have my vector z of the unknown, I can hopefully solve directly for the power spectral density of the response, with including all of the random variables that I have added to assist the problem. And when it comes to flutter, what I can do, I can study the stochastic stability, which is essentially the effect of turbulence on flutter, or the effect of errors in the aerodynamic or elastic loading on flutter, using the concept of moment-Lyapunov exponents in this case, because the problem becomes, unfortunately for me, nonlinear or parametrically nonlinear, even though the turbulence, which is essentially this diffusion term, still is linear. So a few examples just as of this. So my example is the Golden Gate Bridge. I use data from a very old data set, was done by Dr. Jain at Johns Hopkins University. He measured the flutter derivatives. I used the data to then calculate the regression coefficients leading to the initial functions, and this is as the initial function of the torsion mode, or the torsional vibration, if you wish, of the torsional and of the moment as a function of, in this case, the rotation. And why did I choose the Golden Gate Bridge? Because this bridge was interesting and has a relatively low frequencies typical of long span bridges, and I also was not very well designed, and such that the wind speed or the critical wind speed is quite low. This is the original design of the bridge, not after the retrofit of the bridge that followed over the years. And so what I am able to do, which is I'm just showing you an example here, is try to reproduce using this method, the joint probability density function between in this case the torsional response and the torsional velocity in this case. So this is the joint PDF between torsional response and joint velocity, accounting for the title says random modal correlation length, which is nothing else but saying I'm assuming that the correlation of the loads introduced by turbulence is not exactly what I've designed for, but actually I'm trying to assume some sort of variability. What's the catch? The catch is actually it's not always simple to calculate the response using this method. And in order for me to solve this problem, I need to find about 100 numbers or 100 numbers that are needed for me to solve. When it comes to flutter, things become a little bit simpler. By using the so-called moment-Lyapunov exponents, which essentially is a mean to measure over time the stability of a bridge. And these moments can be related to mean square stability or to third moment stability. And theoretically, as the time goes to infinity, if the moment is lower than the zero threshold, then the system is stable, otherwise it's unstable. And this is an example for another type of bridge. This is a 3,000 meter long span bridge, mimicking a little bit the behavior of the Messina Bridge with a much worse design. I designed, in this case, the bridge with a flat plate where the width of the bridge is about 60 meters. My idea was quite bad. As a matter of fact, the flutter wind speed is bad, is very low compared to the actual wind speed of the bridge. But this will enable the possibility of solving this problem in a way that is perhaps not apparent to people. So what we can do, at least for this particular bridge, is solve for flutter in the mean square sense. So it means in the case of the stochastic stability, or it's also in the third moment stability, so beyond the mean square sense, because of the fact that I am now using a model which is nonlinear because of the parametric error perturbation, and I may consider the differences eventually. So on the horizontal axis of this model, what you see essentially, you see the random initial functions, if you want, or some randomness in the aeroelastic load. And the second one is the random modal correlation length, which is nothing else a randomness in the buffeting or in the turbulence of the. So essentially what I'm looking at a combined effect of turbulence and randomness in the aeroelastic forces on the flutter speed. What is my conclusion, at least from this example, was that essentially because of the nonlinear propagation effect, there's a difference between mean square and third moment stability, which means that the critical flutter speed may differ if we just focus on one versus the other. And mean square and third moment stabilities are different from the standard approach, which would be just to look at the mean value for stability. And is there a conclusive reason for believing whether turbulence is detrimental or not, or whether aeroelastic forces are detrimental or not? In general, it's actually not possible, because in the case of mean square stability, as you can see, increasing the randomness in turbulence generates a slight increment of the speed in relative terms, followed by a decrement. But if we look at third moment stability, then turbulence is almost unaffected, if you will, unaffected. So this is an interesting aspect, and so this led to my second eventually lesson, if you want. That is Luca, yes. Can I do? Yeah.
Luca,
sure.
we are running out of time quite badly, I'm afraid. And
so then I'll skip to this one and the last one. So, or maybe I'll skip to the last one then. So I have two more things that I have that I've designed. And so one was on the looking at the Monte Carlo sampling method using a brute force approach for solving for brief flutter response. And the lessons I want to give you is essentially one interesting lessons that we learned, again, in the case of the Golden Bridge, is that we can actually accommodate for climate change effects when we look at flutter analysis. And we can estimate the effects of climate change by looking at flutter speed of, or in terms of expected relative cost, which is the replacement cost of the bridge after collapse, partial or full collapse due to flutter. And so what this picture shows essentially shows the difference between the expected replacement cost due to a presumed or plausible increment of speed due to or worsening of the climate situation over a period of about 50 years, which includes both an increment in the mean arrival rate of the storms and a potential increment of 2% of the wind speed or the design wind speed over 100 years. Combined and concurrent. So this was an interesting aspect that could be considered. The last thing, which is somehow perhaps a little new, I'm going to take maybe a few minutes, is that in recent years, we've looked at problems and way to expedite our analysis. And so we heard from the previous speakers that we may have issues related to long-term need for long-term simulations, either for carrying out buffeting or flutter analysis. So therefore, we looked at the ways to perhaps use artificial intelligence to as an emerging field or as an emerging tool to develop surrogate models for the analysis of flutter and buffeting of bridges. So the basic idea of an artificial neural network is that there is a set of input parameters in a so-called input layer that are then fed forward to the output or the output layer, where these are my outputs. And I can try to replicate any possible nonlinear relationship between input X and output Y by using some appropriately calibrated nonlinear functions that are called transfer functions, mimicking the behavior of the neurons of the brain, essentially. So we apply this idea to a suspension bridge or suspension footbridge, and with that was designed according to a standard finite element problem. And it was because we had access to some data, experimental wind tunnel data of the flutter derivatives from this particular bridge. And these are actually the data. So we carried out some tests in the small scale wind tunnel at Northeastern universities. And this is an example of the H1 star flutter derivative using 30 repeated tests. What we saw is that eventually by repeating the test, variability in the flutter derivatives is observed. Not only that, we could also account for all possible using the data set. We can account for eventually distribution of the parameters, and from which we could use a standard multimode approach. We can predict the flutter speed as a function, in this case, of a modal damping of the true bridge and the frequency of between the torsional and bending mode for the same bridge. So now this is where the artificial intelligence comes to me, is because now what we can do, we can actually look at replicating the same idea using an artificial neural network. So without carrying out the multimode analysis, what we can do, we can actually generate a model-free method to predict the flutter speed you see as a function of a number of input variables, which include, in particular, the scalar derivatives or the flutter derivatives, along with their uncertainty or their variability into the predictions. So these are the results of the artificial neural network. What this curve shows are the target values of the critical speed, the ones that are calculated using the conventional method, versus the outputs that are estimated by the neural network. So there is a procedure that needs to be done here between training, validation, and testing. Of course, we need to have access to a sufficiently large data set, which we have done. And the coefficient of, in this case, the R coefficient of the simulations is quite good. We tried also by expressing the flutter derivatives in a parametric way as a function of essentially as a polynomial, as a function of random coefficients. And these are the coefficients that we derive from the wind tunnel test. They are fully correlated in this case. And then we rerun the same idea instead of using just the data themselves from the experiments. And what we expect is that because simply we are essentially filtering the coefficients, and so we are pre-filtering, if you want, the response when it comes to the neural network is actually better. In other words, the error is actually smaller, and you can see because the coefficient of determination now is almost equal to 1. So to conclude, we did a number of things, and I just presented 2 of them. And we looked at eventually solving the problem in the case of bridge aerodynamics by accounting for various sources of uncertainty, trying to use a method which was a semi-analytical method, both in the case of flutter and buffeting, and it was relatively successful. For what we learned from the stochastic buffeting analysis is that it is possible. However, this method becomes a little problematic for a realistic bridge if we have to account for several modes or eventually several deck modes into the analysis. If we were to look at stochastic flutter, we saw that there is perhaps a difference in flutter velocity that is controlled by turbulence, but especially by variability in the wind tunnel, or if you want, in the initial function or scalar derivatives, and this can lead to about a reduction of 20% of the critical speed. And then at last, I presented the 4th part. I skipped the 3rd one, or I gave just a glimpse. So to use surrogate models based on artificial neural networks and to predict flutter speed of long-span bridges. And the conclusion is that they are quite successful because the yield, now, at least for the examples we ran, was about 90% of the results had an error in terms of flutter speed, which was between 5 to 10%. And which is quite good because we could eventually skip some of these type of analyses, especially when we are dealing with Monte Carlo simulation and to analyze the bridge reliability. So I thank you for your time. I was a little bit long, and I'll be happy to answer any questions, or if you have any questions, just send me an email. Thank you.
Okay, thank you. Could you unshare your screen then, please? Okay. Now, what I propose to do is, we haven't got time, I'm afraid, to ask. I've got quite a lot of questions in front of me. I'm going to put a small number of questions to you, to the speakers, and I'm then going to ask the speakers if they would mind responding in writing over perhaps the course of the next week to the other questions that I will forward on to them.